This presentation is delivered by the Stanford Center for Professional Development.
Okay, so welcome back. And what I want to do today is talk about, is wrap up our discussion on factor analysis. And in particular, what I want to do is step through parts of the derivation for EM for factor analysis, because again, there are a few steps in the EM derivation that are particularly tricky, and there are specific mistakes that people often make on deriving EM algorithms, algorithms like factor analysis. So I want to show you how to do those steps right, so you can apply the same ideas to other problems as well. And then in the second half or so of this lecture, I'll talk about principal component analysis, which is a very powerful algorithm for dimensionality reduction. You'll see later what that means. So just to recap, in the previous lecture, I described a few properties of Gaussian distributions. One was that if you have a random variable, a random value vector x that can be partitioned into two portions, x1 and x2, and if x is Gaussian with mean mu and covariance sigma, where mu is itself a partition vector, and sigma is sort of a partition matrix that can be written like that. So I'm just writing sigma in terms of the four sub-blocks. Then you can look at the distribution of x and ask what is the marginal distribution, right, of say x1. And the answer, excuse me, we said last time was that x1, the marginal distribution of x1 is Gaussian with mean mu and covariance sigma 1, 1, where sigma 1, 1 is the upper left block of that covariance matrix sigma, right? So this one is no surprise. And I also wrote down the formula for computing conditional distributions, such as what is p of x1 given x2. And last time I wrote down that the distribution of x1 given x2 would also be Gaussian with parameters that I wrote as mu of 1 given 2 and sigma of 1 given 2, where mu of 1 given 2 is, let's see, is just this formula times 2. Okay, so with these formulas, we'll be able to look at a pair of joint Gaussian random variables, x1 and x2 here are both vectors, and compute the marginal and conditional distributions of p of x1 or p of x1 given x2. So when I come back and derive the E step, actually, well, I'll come back and use the marginal formula in a second, and then when I come back and derive the E step in the EM algorithm for factor analysis, I'll actually be using these two formulas again. And again, just to continue summarizing what we did last time, we said that in factor analysis, our model, let's see, this is an unsupervised learning problem, and so we're given an unlabeled training set, right, where each xi is a vector in Rn as usual, and we want to model the density of x, and our model for x will be that we imagine there's a latent random variable z that's generating, well, that's just zero mean and identity covariance, and z will be some low dimensional thing d, and we, well, as long as we're, and we imagine that x is generated as mu plus lambda z plus epsilon, where epsilon is a Gaussian random variable with mean 0 and the covariance matrix psi. And so the parameters of this model are mu, which is an n-dimensional vector, lambda, which is an n by d-dimensional vector matrix, and psi, which is n by n, and is diagonal. Is a diagonal and is a diagonal matrix. So I guess the cartoon I drew last time for factor analysis was, I said that maybe that's a typical example of data point zi if, and in this example I had d equals 1, n equals 2, right? So z in this example is one-dimensional, d equals 1, and so you take this data, map it to, say, some mu plus lambda z, and that may give you some set of points there. And lastly, this model was envisioning that, you place a little Gaussian bump around each of these, say, and sample. Let's change chalk colors. And the x's are then maybe that would be a typical sample of the x's under this model. Okay. So right. So how do we fit the parameters of this model? Well, the joint distribution of z and x, is actually Gaussian with parameters given by some vector that I wrote as mu xz and some covariance matrix sigma. And if you write out what those two things are, this vector mu xz is a vector of zeros appended to the vector mu, and the matrix sigma is this partitioned matrix. Okay, we also worked this out last time. So you can ask, what's the distribution of x under this model? And the answer is, well, under this model, x is Gaussian with mean mu and covariance lambda lambda transpose plus psi, right? So it's just, take the second block of the mean vector and take that lower right-hand corner block of the covariance matrix. And so this is really my formula for computing the marginal distribution of a Gaussian, except that I'm computing the marginal distribution of the second half of the vector rather than the first half. Right? So this is the marginal distribution of x under my model. And so if you want to learn, yeah.
So for the initial distribution you had, that's the conditional?
Excellent.
Yeah.
Let's see. Oh yes, yes. So on this board, I'm writing down the right. This is really specifying the conditional distribution of x given z. Right. So the conditional distribution of x given z. This is Gaussian with mean mu plus lambda z and covariance psi. So this is what that's specifying. Right. Yeah. Okay. So since this is the marginal distribution of x, given my training set of m unlabeled examples, I can actually write down the log likelihood of my training set, right? So, the log likelihood of my training set is, actually, let me just write down the likelihood, right? So the likelihood of my parameters given my training set is the product from I equals 1 to m of p of xi, given the parameters, right? And I can actually write down what that is because xi is Gaussian with parameter mu and variance lambda lambda transpose times psi. So you can just write this down as, 1 over 2 pi to the n over 2, the determinant of, right, and then times e to the minus 1/2, x, right? So that's my formula for the density of a Gaussian that has mean mu and covariance lambda lambda transpose plus psi. Okay? So this is my likelihood of the parameters given a training set. And one thing you could do is actually take this likelihood and try to maximize it in terms of the parameters. Try to find the maximum likelihood estimate of the parameters. But if you do that, you find that if you sort of try, take logs to get the log likelihood, take derivatives, set derivatives equal to 0, you find that you'd be unable to solve for the maximum of this analytically. Right? And so you won't be able to solve this maximum likelihood estimation problem. If you take the derivative of this with respect to the parameters, set the derivatives equals to 0, and try to solve for the value of the parameters lambda, mu, and psi that maximizes. You won't be able to do that. And go and try to do it. So what we'll use instead to estimate the parameters in our factor analysis model will be the EM algorithm. Yeah.
Why is the log likelihood p of x and not like p of x given p of x and z or something?
Oh, right. Okay. So question is, why is the likelihood p of x and not p of x given z or p of x and z? So the answer is, let's see, we're in an so by analogy to the mixture of Gaussian distributions models, we're given a training set that just comprises an unlabeled training, a set of unlabeled training examples. But for convenience, for whatever reason, it's easier for me to write down a model that defines a joint distribution on p of x comma z. But what I would like to do is really maximize, as a function of my parameters, I'm using theta as a shorthand to denote all the parameters of the model. I want to maximize the probability of the data I actually observed. And this would be actually max over theta, product from I equals 1 to m. And this is really integrating out z. Okay, so I only ever get to observe the x's, and the z's are latent random variables or hidden random variables. And so what I like to do is do this maximization in which I've sort of implicitly integrated out z. Does that make sense? Okay, cool. Are there other questions about the factor analysis model? Okay. So here's the EM algorithm. Right. In the E step, we compute the conditional distribution of Zi given Xi and our current setting of the parameters. And in the M step, and in the M step, we perform this maximization. And if this looks a little bit different from the previous versions of EM that you've seen, the only difference is that now I'm integrating over ZI, because ZI is now a Gaussian random variable. It's now this continuous value thing. So rather than summing over ZI, I now integrate over ZI. And if you replace this integral over sum, get rid of the dZi, then this is exactly the M step you saw when we worked it out for the mixture of Gaussians model and the other models. So it turns out that in order to implement the E step and the M step, there are just two little things. Actually, there are actually sort of three key things that are different from the models that you saw previously. So I want to talk about them. The first one is that the first of the three is maybe the simplest, which is that in the E step, Z is now a continuous value random variable. And so you now need a way to represent these continuous value densities, probability density functions, to represent Qi of Z. So fortunately, in this problem is not difficult to do. And in particular, right, the conditional distribution of Zi given Xi and our parameters, which I'm going to omit from this equation, is going to be Gaussian with mean and covariance given by, these two things that I write like that, where this is going to be equal to the vector 0 minus and the way I got this formula was if you match this to the formula I had previously for computing conditional distributions of Gaussians, this corresponded to the terms mu1 minus sigma1 to sigma2 to inverse times x2 minus mu. Okay, so those are the terms corresponding to the formula I had previously for computing the marginal distributions of a Gaussian. And that is going to be given by, that, and again, those are the terms corresponding to the formulas I had for the very first thing I did, the formulas for computing conditional distributions of Gaussians. Okay, and so this is E step. You need to compute the Q distribution. You need to compute, excuse me, Qi of Zi. And to do that, what you actually do is you compute this vector mu of Zi given Xi and sigma of Zi given Xi. And together, these represent the mean and covariance of the distribution Q, where Q is going to be Gaussian. So that's the E step. Now, here's the M step then. And let's mention there are sort of two ways to derive M steps for especially Gaussian models like these. And here's the key trick, I guess, which is that when you compute the M step, you often need to compute integrals that look like these. Right? And then there'll be some function of Zi. And let me just write Zi there, for instance. Right? So there are two ways to compute integrals like these. One is if you write out, this is a commonly made mistake well, not mistake, commonly made unnecessary complication, I guess. One way to try to compute this integral is you can write this out as integral over Zi. And well, we know what Qi is, right? Qi is a Gaussian, so, 2 pi to the d over 2. The covariance of Qi is this sigma given Xi, right? Which you've computed in the E step, and then times e to the minus 1/2 Zi minus mu of Zi given Xi, transpose sigma inverse times So that's my Gaussian density, and then times Zi dZi. Okay? And so writing this out is the unnecessarily complicated way to do it, because once you've written out this integral, if you want to, actually integrate, that's the times, right? It's multiplication. If you actually want to evaluate this integral, it just looks horribly complicated. I'm not quite sure how to evaluate this. By far, the simpler way to evaluate this integral is to recognize that this is just the expectation with respect to Zi drawn from the distribution Qi of the random variable Zi. And once you write it out this way, you notice that, well, this is just the expected value of Zi under the distribution Qi. But Qi is a Gaussian distribution, with mean given by that mu vector and covariance given by that sigma vector. And so the expected value of Zi under this distribution is just mu of Zi given Xi. Okay? Does that make sense? So by making this observation that this is just an expected value, this is a much easier way to compute that integral. So it's counting on time. Yeah. So we'll apply the same idea to the M step. So in the M step, we want to maximize this. Right. There's also sum over I. There's also summation over I outside, but this is essentially the term inside the argmax of the M step, where I've taken the integral of a Zi and just observed that that just corresponds to an expectation with respect to the random variable Zi of this thing inside. And so this simplifies to the following. Okay. And it turns out, actually, all I did here was use the fact that, P of x given z times P of z equals P of x comma z, right? That's just combining this term and that term gives you the numerator in the original. And so it turns out that for factor analysis, in these two terms, this is the only one that depends on the parameters. The distribution P of Zi has no parameters because Zi was just drawn from a Gaussian with zero mean and identical variance. Qi of Z was this fixed Gaussian. It doesn't depend on the parameters theta. And so in the M step, we really just need to maximize this one term with respect to our parameters, mu, lambda, and psi. Okay. So let's see. Yeah. There's sort of one more key step I want to show, but to get there, I have to write down sort of an unfortunately large amount of math. But let's go into it. Okay. So in the M step, we want to maximize and all expectations with respect to Zi drawn from the distributions Qi. And sometimes I'll be sloppy and just omit this. And now, this distribution, right, P of xi given zi, that is a Gaussian density because, you know, xi given zi, this is Gaussian with mean given by, right, mu plus lambda z and covariance psi. And so in this step of the derivation, I will actually go ahead and substitute in the formula for the Gaussian density. So I will go ahead and take this and, you know, plug into here 1 over 2 pi to the n over 2 psi inverse e to the dot dot dot. Okay, so I will go ahead and plug in the Gaussian density. And when you do that, you find that you get expectation. Oh, excuse me. Right, I forgot to say, to maintain sort of, I don't know, to not make the derivation too complicated, I'm actually just going to maximize this with respect to the parameters lambda. Okay, so let me just show how to, so you want to maximize this with respect to lambda, psi, and mu, but just to keep the amount of math I'm going to do in class sane, I'm just going to show how to maximize this with respect to the matrix lambda, and I'll pretend that psi and mu are fixed. Okay, and so if you substitute in the Gaussian density, you get some expected value of a constant. The constant may depend on psi, but not on lambda. Then minus this thing. Okay, and this quadratic term essentially came from, you know, the exponent in your Gaussian density. When I take log of exponent, then you end up with this quadratic term. And so if you take the derivatives of the expression above, with respect to the matrix lambda, and you set that to 0, right? So we want to maximize this expression with respect to the parameters lambda. So you take the derivative of this with respect to lambda. Oh, excuse me. It's a minus sign. And set the derivative of this expression to 0. Set derivatives equal to 0 to maximize things, right? When you do that and simplify, you end up with the following. Okay, and so that's the, in the M step, this is the value you get. This is the value you should get, yeah, that you use to update your parameters lambda. And again, the expectations are with respect to zi drawn from the distributions qi, right? So the very last step of this derivation is we need to work out what these two expectations are. And so the very first term, you know, EZI transpose, I guess, is just mu of ZI given XI transpose because the QI distribution has mean given by this and right. To work out the other term, let me just remind you, I guess, that if you have a random variable z that's Gaussian with mean mu and covariance sigma, then the covariance matrix sigma is EZZ transpose minus EZ transpose. Right. That's, one of the definitions of the covariance. And so this implies that EZZ transpose equals sigma plus EZ transpose. And so the second term here becomes sigma Zi given mu I plus given xi. Okay. And so that's how you compute E of Zi transpose and E of Zi transpose and substitute them back into this formula. And you would then have your m-step update to the parameter matrix lambda. And the last thing I want to point out in this derivation is that it turns out it's partly because of the name EM algorithm, expectation maximization. One common mistake for the EM algorithm is in the E step, someone to take the expectation of the random variable z, and then in the M step, to just plug in the expected value everywhere you see it. Right? So in particular, one common mistake in deriving EM for factor analysis is to look at this and say, oh, look, I see ZZ transpose. Let's just plug in the expected value under the Q distribution. And so we'll plug in that, right? Mu of Zi given Xi times mu of Zi given Xi transpose into that expectation. and this is an incorrect error. And that would be an incorrect derivation of EM. And because it's missing this other term, sigma of Zi given Xi. Okay, so one common misconception for EM is that in the E step, you just compute the expected value of the hidden random variable, and the M step, you plug in the expected value. And it turns out in some algorithms, that turns out to be the right thing to do. In the mixture of Gaussians and in the mixture of naive Bayes models, that would actually give me the right answer. But in general, the EM algorithm is more complicated than just taking the expected values of the random variables and then pretending that they were sort of observed at the expected values. Okay, so I want to go through this just to illustrate that step as well. And so just to summarize, the three key things to keep in mind that came up in this derivation were, one, for the E step, we had a continuous Gaussian random variable. And so to compute the E step, we actually compute the mean and covariance of the of the distribution Qi. The second thing that came up was in the M step, when you see these integrals, sometimes if you interpret that as an expectation, then the rest of the math becomes much easier. And the final thing was, again, in the M step, the EM algorithm is derived by a certain maximization problem that we saw. And is not necessarily just plugging the expected value of Zi everywhere. Okay. Let's see. Okay. I feel like I just did a ton of math and wrote down way too many equations. And even doing this, I was skipping many steps. So you can go to lecture notes to see, all the steps, all the derivations of the steps I skipped, like how you actually take derivatives with respect to the matrix lambda, and how to compute the updates for the other parameters as well, for mu and for psi, since this is only for lambda. And so that's the factor analysis algorithm. Justin?
I was just wondering, in the step in the lower right board, where we said that I guess the second term doesn't have any parameters that we're interested in. The first term has all the parameters, so we'll just drop the second term. But it seems to me that Qi has a lot of parameters.
Let's see, right. Let's see. So the question was right. So doesn't the term Qi have parameters, right? So so in the EM algorithm, Qi is it actually turns out in the EM algorithm, sometimes P of Zi may have parameters, but Qi of Zi may never have any parameters. In the specific case of factor analysis, P of Zi doesn't have parameters. In other examples, in a mixture of Gaussians, models say Zi was a multinomial random variable, and so in that example, P of Zi had some parameters. But it turns out that Q of Zi will never have any parameters. And in particular, Qi of Zi is going to be is this Gaussian distribution, right? Is Gaussian with mean given by mu of Zi given xi and covariance, sigma Zi given xi. And so it's true that mu and sigma may themselves have depended on the values of the parameters I had in the previous iteration of EM. But the way to think about Q is I'm going to take the parameters from the previous iteration of the algorithm and use that to compute what Qi of Zi is. And that's the E step in the EM algorithm. And then once I've computed what Qi of Z is, then this is a fixed distribution. And I'm going to use these fixed values for mu and sigma and just keep these two values fixed as I run the M step. Okay.
So those, okay, I guess I was confused because in the
yeah.
the second port over, there's a lot of, it looks like there are parameters, but I guess they're old iterations of the parameters.
Yeah, yes, you're right. Yeah. When I wrote down Qi of Zi, it was a function of the parameters from the previous iteration, and I want to compute the new setting of parameters. Cool. Are there more questions? Okay, cool. Boy. So this is probably the most math I'll ever do in a lecture in this entire quarter. So, let's now talk about a different algorithm. Actually, which board was I on? So, this one. So what I want to do now is talk about an algorithm called principal components analysis. Which is often abbreviated PCA. And here's the idea. PCA has a very similar motivation as factor analysis, but it sort of maybe gets at the problem a little bit more directly than just factor analysis. So the question is, given, right, so we're still doing unsupervised learning. So given a training set of m examples where each xi is an n-dimensional vector as usual, what I'd like to do is reduce it to a lower dimensional data set where k is strictly less than n, and often and quite often it'll be much smaller than n. So I'm going to give a couple examples of why we want to do this. Imagine that you're given a data set that contains measurements, and unknown to you, I don't know, measurements of, I don't know, people or something. And unknown to you, whoever collected this data actually included the height of the person in centimeters as well as the height of the person in inches. And so because of rounding off to the nearest centimeter or rounding off to the nearest inch, the values won't exactly match up, but along 2 dimensions of this data anyway, it'll lie extremely close to a straight line, right? But it won't lie exactly on a straight line because of rounding off to the nearest centimeter or inch, but lie very close to a straight line. And so we have a data set like this. It seems that what you really care about is that axis, right? And this is sort of really, this axis is really the variable of interest. That's maybe the closest thing you have to the true height of a person. And this other axis is just noise, okay? And so if you can reduce the dimension of this data from two-dimensional to one-dimensional, then maybe you can get rid of some of the noise in this data. And quite often, you won't know that this was cm and this was inches. You may have a data set with 100 attributes, but you just didn't happen to notice one was cm and one was inches. Right? Another example that I sometimes think about is, some of you know that my students and I work with autonomous helicopters a lot, right? And so we imagine that you take surveys or quizzes or measurements of radio-controlled helicopter pilots. Maybe one axis you have measurements of your pilot skill, of how skillful your helicopter pilot is, and on another axis maybe you measure how much they actually enjoy flying, and maybe this is actually roughly one-dimensional data, and there's some intrinsic variable of interest, which I'll call maybe pilot aptitude, that somehow determines their skill and how much they enjoy flying something. And so again, if you can reduce this data from two dimensions to one-dimensional, maybe you have a slightly better measure of what I'm calling loosely pilot aptitude, which may be what you're really wanting to capture. Okay, so let's talk about an algorithm to do this, and I should come back and talk about more applications of PCA later. So here's the algorithm. Before running PCA is normally you pre-process the data as follows. I'll just write this out, I guess. Okay, so okay, let's let some of you, I know some of you are writing. Well, okay, so this is maybe just a unnecessary amount of writing to say that, compute the mean of my training set and subtract out the means. So now I've zeroed out the mean of my training set. And the other step is I'll compute the variance of each of my features, after zeroing out the mean. And then I'll divide each feature by the standard deviation so that each of my features now has equal variance. So these are standard pre-processing steps we'll often do for PCA. I'll just mention that sometimes the second step is usually done only when your different features are on different scales. So if, I don't know, if you're taking measurements of people, and so, one feature may be their height, then another may be their weight, another may be their strength, another may be, I don't know, their age or whatever. All of these quantities are on very different scales, and so you normally normalize the variance. Sometimes if all the xi's are the quote same type of thing, so for example, if you're working with images and the xij's are the pixels of different, are on the same scale because they're all pixel intensity values ranging from 0 to 255, then you may omit this step. Okay. So after pre-processing, let's talk about how we would find the main axes along which the data varies, or how we find the principal axes of variation of the data. And And so to do that, let me just go through one specific example and then we'll formalize the algorithm. So okay, here's my training set comprising 5 examples, and it has roughly 0 mean. So, and the variance on the x1 and x2 axes are the same. That's x1, that's my x2 axes. And so, the principal axis of variation of this data is roughly the positive 45-degree axis, right? So what I'd like to do is have my algorithm conclude that this direction that I've drawn with this arrow u is sort of the best direction onto which to project the data. So that the axis by which my data really varies. So let's think about how we formalize that, right? Well, one thing I want to look at is suppose I take that axis. This is really the axis onto which I want to project on that I want to use to capture most of the variation of my data. And then when I take my training set and project it onto this line, right? Then I get that set of points. Okay. And so you notice that those dots, the projections of my training set onto this axis, has very large variance, right? In contrast, if I were to choose a different direction, let's say this is really the orthogonal and the worst direction onto which to project my data. If I project all my data onto this axis, right, then I find that the projections of my data onto the purple line, onto this other line, has much smaller variance. Then my points are clustered together much more tightly. Okay? So one way to formalize this notion of finding the main axis of variations of data is I would like to find the vector u, or I'd like to find the direction u, so that when I project my data onto that direction, the projected points vary as much as possible. So in other words, I'm going to find a direction so that when I project my data onto it, the projections are largely are widely spaced out. There's large variance. Okay. So let's see. So I want to find the direction u, and just as a reminder, if I have a vector u of norm 1, then the length of a vector xi projected, well, then a vector xi projected onto u, has length xi transpose u, right? This is to project a vector onto to project x onto a unit vector, the length of the projection is just xi transpose u. And so to formalize my PCA problem, I'm going to choose a vector u to maximize, right? So I choose u, and this is subject to the constraint that the norm of u, that the length of u is 1. But I'm going to maximize, let's see, sum from I equals 1 to m. The length of the projection of the vectors x onto u. Okay? In particular, I want the sum of squared distances of the projections to be far from the origin. I want the projections of x onto u to have large variance. And just to simplify some of the math later, let me put a 1 over m in front. And so that quantity on the right is equal to 1 over m, so from let's see, u transpose xi times xi transpose u, right? And so you can simplify, and I get this is U transpose times transpose U. Okay. So I want to maximize U transpose times some matrix times U, subject to the constraint that the length of U must be equal to 1. And so some of you recognize that this means U must be the principal eigenvector of this matrix in the middle, right? So let me just write that down. I'll say a few more words about it. So this implies that U is the principal eigenvector of the matrix. And I'll just call this matrix sigma. It actually turns out to be a covariance matrix. Sum from I equals 1 to m transpose. Okay. Actually, let's check. How many of you are how many of you are familiar with eigenvectors? Wow, cool. Most of you, almost all of you. Great. Yeah. Well, what I'm about to say is very extremely familiar, but it's worth saying anyway. Right. So if you have a matrix A and you have a vector U, and they satisfy AU equals lambda U, then this is what it means for U to be an eigenvector of the matrix A. And the value lambda here is called an eigenvalue. Right? And so the principal eigenvector is just the eigenvector that corresponds to the largest eigenvalue. One thing that some of you may have seen, but I'm not sure that you have, and I just want to relate this to stuff you already know as well, is that you know, an optimization problem is really maximize U transpose U subject to the norm of U is equal to 1, right? And let me write that constraint as that U transpose U equals 1. And so to solve this sort of, you know, constrained optimization problem, you write down the Lagrangian minus lambda, right? Where that's the Lagrange multiplier. Right? And so because this is a constrained optimization, right? And so to actually solve this optimization, you take the derivative of L with respect to U, and that gives you sigma U minus lambda U. You set the derivative equal to 0, and this shows that sigma U equals lambda U, and therefore the value of U that solves this, you know, constrained optimization problem we care about must be an eigenvector of sigma, and in particular it turns out to be the principal eigenvector. Okay. So just to summarize, what have we done? We've shown that given a training set, if you want to find the principal axis of variation of data, if you want to find, you know, the 1D axis on which the data really varies the most, what we do is we construct the covariance matrix sigma, the matrix sigma that I wrote down just now, and then you would find the principal eigenvector of the matrix sigma. And this gives you the best 1D subspace onto which to project your data. And more generally, you would choose And more generally, if you want a k-dimensional subspace onto which to project your data, you would then choose U1 for UK to be the top k eigenvectors of sigma. And by top k eigenvectors, I just mean the eigenvectors corresponding to the k highest eigenvalues. I guess I showed this only for, for the case of a 1D subspace, but this holds more generally. And now the eigenvectors U1 for UK represent, sort of give you a new basis with which to represent your data. Okay? So, yeah.
Is there a restriction on a different axis that has to be orthogonal?
Let's see. So by convention, PCA will choose orthogonal axes. Yeah, right. So, maybe this is worth saying. So here's just one more example. Imagine that you have a three-dimensional data set. And imagine that your three-dimensional data set, it's very hard to draw in 3D on the board, so let me try this. Imagine that my x1 and x2 axes lie in the plane of the board, and the x3 axis points directly out of the board, right? So imagine that you have a data set where most of the data lies on the plane of the board, but there's just a little bit of fuzz. So imagine that the x3 axis points orthogonally out of the board, and all the data lies roughly in the plane of the board, but there's just sort of like a tiny little bit of fuzz so that some of the data lies just a couple of millimeters off the board, right? So if you run PCA on this data, you find that U1 and U2 will be some pair of bases that essentially lie in the plane of the board, and U3 will be an orthogonal axis that points roughly out of the plane of the board. Okay. So if I reduce this data to 2 dimensions, then the bases U1 and U2 now give me a new basis with which to construct my lower dimensional representation of the data. Just to be concrete about what that means, previously we had right? We have, say, fairly high dimensional input data xi and rn. And now, if I want to represent my data in this new basis given by U1 up to UK, is that I would take each of my original training examples xi, and I would now represent it or replace it with a different vector, which I call yi, and that will be computed as u1 transpose x I, u2 transpose xi. Okay, and so the yi's are going to be k-dimensional, where k will be less, your choice of k will be less than n. So this represents a low dimensional representation of your data. And this represents sort of an approximate representation of your original data, where you're using only k numbers to represent each training example rather than n numbers. Let's see. Yeah, okay. Yeah.
Not to have eigenvectors and have some sort of trivial eigenvectors?
Is it possible to not have eigenvectors but have trivial eigenvectors?
Yeah, it's only determined by your data sampling. Is that a condition where you need to restrict the type of data?
Let's see, what do you mean by trivial eigenvectors? Oh, okay, yes. So I see. Yeah. So let me see if I can get this right. So there's some matrices that are I think it's almost degenerate, that don't have a full set of eigenvectors. Sorry, deficient, I think is what it's called. Is that right, Zico? Yeah. So there's some matrices that are deficient and actually don't have a full have a full set of eigenvectors. So then we, like an n by n matrix that does not have n distinct eigenvectors. But that turns out not to be possible in this case because the covariance matrix sigma is symmetric, and symmetric matrices are never deficient. So the matrix sigma will always have a full set of eigenvectors. It's possible that, you know, if you, yeah. There's one other issue, which is repeated eigenvalues. So for example, it turns out that in this example, if my covariance matrix looks like this, right, you know, 0.01, I guess, right? It turns out that the identity of the first two eigenvectors is ambiguous. And by that I mean you can choose this to be U1 and this to be U2, or I can just as well rotate these eigenvectors. I can choose that to be U1 and that to be U2, or even, you know, choose that to be U1 and choose that to be U2, and so on. And so when you apply PCA, one thing to just keep in mind is sometimes eigenvectors can rotate freely within their subspaces when you have repeated eigenvalues or close to repeated eigenvalues. And so the way to think about the vectors U is think of it as a basis with which to represent your data, but you know, the basis vectors can sometimes rotate freely, and so it's not always useful to look at the eigenvectors one at a time and say, you know, this is my first eigenvector and it's capturing whatever, the height of the person. This is my second eigenvector, it captures the skill at this task or whatever. That's a very dangerous thing to do when you look at when you do PCA. What is meaningful is the subspace spanned by the eigenvectors, but looking at the eigenvectors one at a time is sometimes a dangerous thing to do. Okay? Because they can often rotate freely, or tiny numerical changes can cause eigenvectors to change a lot. But the subspace spanned by the top k eigenvectors will usually be about the same. All right. So, actually turns out there are multiple possible interpretations of PCA. I'll just give one more without proof, which is that you know, whatever. Given a training set like this, another view of PCA is, and let me just choose the direction. This is not the principal components, right? And choose some direction and project my data onto it. This is clearly not the direction PCA would choose. But what you can think of PCA as doing is choose a subspace onto which to project your data so as to minimize the sum of squares differences between the projections and the original points. So in other words, another way to think of PCA is trying to minimize the sum of squares of these distances between, you know, the dots, the points x and the dots onto which I'm projecting the data. And it turns out there are actually, I don't remember, there's sort of like 9 or 10 different interpretations of PCA, and this is another one. There are a bunch of ways to derive PCA, and you get to play with sort of PCA ideas more in the next problem set. What I want to do next is talk about a few applications of PCA. So here are some ways that PCA is used. One is visualization, right? Very often you have high-dimensional data sets. And someone gives you like a 50-dimensional data set, and it's very hard for you to look at the data set that's 50-dimensional and understand what's going on, because you can't plot something in 50 dimensions. So common practice, if you want to visualize a very high-dimensional data set, is to take your data and project it into, say, a 2D plot, or project into a 3D plot, so you can render like a 3D display on your computer, so you can better visualize the data and look for structure. One particular example that I learned about of doing this recently was in Krishna Shenoy's lab here in Stanford, in which he he had readings from 50 different parts of a monkey brain. I actually don't remember it was the number 50, but so tens of parts, different parts of a monkey brain. And so, you'd have this 50-dimensional readings, 50-dimensional vectors correspond to different amounts of electrical activity in different parts of the monkey brain. It was actually 50 neurons, but tens of neurons. But it was sort of tens of neurons in the monkey brain, and so you have a 50-dimensional time series. And it's very hard to visualize this very high-dimensional data. But what he and the students did was use PCA to project this 50-dimensional data down to 3 dimensions. And then you can visualize this data in 3 dimensions of just using a 3D plot. And so you could sort of visualize what the monkey is thinking over time. So that was cool. Another common application of PCA is compression. Right? So if you have high-dimensional data and you want to store it with fewer real numbers, clearly PCA is a great way to do this. It turns out also that sometimes in machine learning, sometimes you're just given extremely high-dimensional input data, and for computational reasons, you don't want to deal with such high-dimensional computation data, such high-dimensional data, right? And so, one common use of PCA is to take a very high-dimensional data and represent it, with a low-dimensional subspace. Is that yi is the representation I wrote down just now, so that you can work with much lower-dimensional data, and it turns out to be, sort of just seems to be like a fact of life that when you're given extremely high-dimensional data, almost all the time, just in practice, of all the very high-dimensional data sets I've ever seen, very high-dimensional data sets often have all their points lying on much lower-dimensional subspaces. So very often you can dramatically reduce the dimension of your data and really not be throwing too much of the information away. Let's see, right. So if you're learning an algorithm that takes a long time to run on very high dimensional data, you can often use PCA to compress the data to a low dimension so that your learning algorithm runs much faster. And you can often do this with sacrificing almost no performance in your learning algorithm. There's one other use of PCA for learning, which is, you remember when we talked about learning theory, we said that the more features you have, the more complex your hypothesis class. If, say, you're doing linear classification, right? If you have more features, you have lots of features, then you may be more prone to overfitting. So one other thing you could do with PCA is just use that to reduce the dimension of your data so that you have fewer features and you're maybe slightly less prone to overfitting. This particular application of PCA to learning, I should say, it sometimes works, it often works. I'll actually later show a couple of examples where you sort of do this and it works. But this particular application of PCA, I find, when you look in the industry, it also seems to be a little bit overused. And in particular, actually, let me say more about that later. I'll come back to that later. So one couple of other applications to talk about. One is outlier detection or anomaly detection. Right? And so the idea is, suppose I give you a data set, you may then run PCA to find, roughly the subspace on which your data lies. And then if you want to find anomalies in future examples, you can then just look at your future examples and see if they lie very far from your subspace. Right? So this isn't a fantastic anomaly detection algorithm. It's not a very good anomaly. Right? So the idea is if I give you a data set, you may find a low-dimensional subspace on which it lies, and then if you ever find a point that's far from your subspace, you can flag that as an anomaly. So this really isn't the best anomaly detection algorithm, but sometimes this is done. And the last application that I'm going to sort of go into a little bit more in detail is matching, or to find better distance calculations. So, and let me say what I mean by this. And I'll go into much more detail on this last one. So here's the idea. Let's say you want to do face recognition. need to use my laptop later. Just make sure it's, well, let me just wake this up first. Okay. So let's say you want to do face recognition, and you have 100 by 100 images, right? So, you know, picture of a face is like whatever, right? Some array of pixels, and the pixels have different grayscale values, and depending on, you know, the different grayscale values, you get different pictures of people's faces, right? And so just make sure my laptop's awake. Okay. So if you have 100 by 100 pixel images, then think of each face as a 10,000 dimensional vector, which is very high dimensional. And useful cartoon to keep in mind, and think of, you know, here's my plot of my 100 dimensional space, right? And if you look at a lot of different pictures of faces, you know, each face will be some point in this 100,000 dimensional space. And in this cartoon, I want you to think of it as maybe most of this data lies on a relatively low dimensional subspace, because in this 10,000 dimensional space, really not all points correspond to valid images of faces, right? The vast majority of values, the vast majority of sort of 10,000 dimensional images just correspond to random noise-like looking things and don't correspond to a valid image of a face. But instead, the space of possible face images probably spans a much lower dimensional subspace. Okay? Shoot. My laptop's not waking up for some reason. Let me see if I'm... Sorry. Okay, let's see if this works. Oh, okay. And so what we'll do is we'll use PCA to find the low dimensional subspace on which the data lies. And in practice, PCA dimension of 50 would be fairly typical. And right, so think of, you know, there's some axes that really measure the shape or the appearance of a face. And there are some other axes that we're not interested in that are maybe just, you know, random noise. So what we'll do is, for face recognition, I might give you a picture of a face and ask you what face looks the most similar to this. And we give you a picture of someone and ask you, can you find other pictures of the same person? And so, you know, the key step to do that, right, is to look at two faces and to compare how similar these two faces are. So, okay. And so here's how we'll use PCA. Given a face there and a different face there, the way I measure the distance between these two faces is I won't just measure the Euclidean distance similarity. Instead, I'll take this face and project it onto my 50-dimensional subspace. And take this, project it onto my 50-dimensional subspace, and measure the similarity between those 2 points in the subspace. Okay? And so when I do that, I may end up with, you know, a face here and a face here that look very far apart in the original space, but when I project them onto the subspace, they may end up looking much more similar. So what I want to show you in a second on the laptop is, let's see, you know, given each of these training examples, right, as a 10,000 dimensional vector, I can plot that as a grayscale image, and I get like a picture of some person's face. What I'll also show you on the laptop will be plots of my eigenvectors. And so the eigenvectors also live in the 10,000 dimensional subspace. And I plot that, you get, you know, some image that's, and these images are called eigenfaces. And what PCA is doing is essentially using linear combinations of these eigenface images to approximate these xi's. And there's these eigenfaces that span, so that these bases, U1, U2, and so on, that span, hopefully, the subspace along which my faces live. Okay, so can I just bring down the laptop display, please? boy. Sorry about running a bit late. I'm not sure what my laptop's doing. Gee. Still seems to be slowly. Okay, nearly there. Yeah, I have no idea why it's taking so long to start it right now. But there. All right, yeah. And our TA Paul spent a lot of time in the middle of the last night preparing some of these images, so better show them all. Okay, cool. So here's a training set comprising aligned images like these, much larger set than is shown here. And so when you run PCA, these are some of the plots of the UIs. So remember I said plot the eigenvectors UI in the same way that it's plotting the training examples. And so you end up with the eigenvectors being sort of grayscale images like these, and will approximate images of faces with linear combinations of these. So I said it's dangerous to look at individual eigenvectors, but and you really shouldn't do that. But let me just do that a little bit anyway. So if you look at the first eigenvector, this corresponds roughly to whether the face is illuminated from the left or the right. So depending on how heavy the weight is on this image, that roughly captures variation in illumination. Second image is hard to tell. It seems to be capturing variation in overall brightness of the face. The third eigenvector capturing roughly how much of a shadow or maybe a beard or something the person has, and so on. And it's dangerous to look at individual eigenvectors, but it's sort of just slightly informed to look at it. Here's an example of a specific application of eigenfaces. So this is from Alex Pentland's lab in MIT. In this display, this upper leftmost image is the input to the eigenfaces algorithm. And the algorithm is then asked to go through a database and find the most similar faces. And so, this second image here is what it thinks is the most similar face to the input. The next one over is the second most similar. The next one over is the third most similar, and so on. And so using eigenfaces and by measuring distances between faces in that low dimensional subspace is able to do, a reasonable job identifying pictures of the same person, even sort of with faces of the person removed. Oh, and the next row shows the next most similar face, and so on. So this one is the fourth most similar face, and so on. This is one more different. Okay, so it's a useful application of eigenfaces. The last thing I want to say is just when people tell me about machine learning problems, I do often recommend they try PCA for different things. So PCA is a useful thing to know to use for compression, visualization, and so on. But in industry, I just tend to see sometimes PCA used slightly more often than, there are also some times where you see people using PCA when they really shouldn't. So just one final piece of advice for use of PCA is before you use it, also think about whether you could just do it with the original training data XI without compressing it, since I've also definitely seen people compress the data when they really did need to. But having said that, I also often advise people to use PCA for various problems. It also works. Okay, sorry about running late. Let's wrap up for today then.